Lesson 4. Elastic and inelastic collisions. Recall from last lesson the definition of isolated system. An isolated system is one where there's no external net force. This means there's no air drag, friction, or applied forces in the system. An isolated system is one where there's no energy loss due to air drag, friction, or applied forces. Because of this, the law of conservation of energy applies. This means that the total energy before a collision is equal to the total energy after a collision. Conservation of momentum will also apply in an isolated system. This means the total momentum before a collision is equal to the sum of the total momentum after a collision. This is always true as long as we have an isolated system. Now, when we say energy in the law of conservation of energy, what we're actually referring to is the total energy. The energy within a system could be transferred or transformed to other objects or to other forms of energy. So we can't necessarily expect the kinetic energy to remain the same before and after a collision. Kinetic energy could be transformed into other forms of energy. The kinetic energy is given by the formula EK equals 1/2 mv squared. And while the total energy, which includes in some part kinetic energy, is the same before and after a collision, the total kinetic energy isn't necessarily conserved. There are two kinds of collisions: elastic collisions and inelastic collisions. An elastic collision is one where the kinetic energy is conserved. This means the sum of the kinetic energies before a collision is equal to the sum of the kinetic energies after the collision for an elastic collision. An inelastic collision is one where the kinetic energy is not conserved. Some of the kinetic energy may be lost as it's transformed to other energy forms during the collision. This means the sum of the kinetic energies before a collision is not equal to the sum of the kinetic energies after a collision in the inelastic collision. We'll start with an example. For billiard balls A and B below, find the velocity of B after the collision and determine if the collision is elastic or inelastic. We'll start by applying the law of conservation of momentum to find the velocity of ball B. The law of conservation of momentum says the sum of the momenta before the collision is equal to the sum of the momenta after the collision for an isolated system. This means momentum of ball A before the collision plus momentum of ball B before the collision equals the momentum of ball A after the collision plus the momentum of ball B after the collision. Since momentum is given by the formula mass times velocity, momentum of ball A is its mass times its velocity. This is a positive 4 meters per second because it's going to the right. The momentum of ball B is 0.3, and since ball B is not moving, its velocity is 0. After the collision, momentum of ball A is 0.5 times its new velocity after the collision, and ball B is 0.3 kilograms times its unknown velocity, which we'll write as velocity of ball B after the collision. This gives us 0.5 times 4 is 2, plus 0.3 times 0 is 0, equals 0.5 times 1 is 0.5, plus 0.3 velocity of ball B after the collision. This gives us the velocity of ball B after the collision equal to 5 meters per second. Now that we know the velocity of ball B after the collision, we can determine whether it was an elastic or inelastic collision by looking at the kinetic energies. The sum of the kinetic energy before the collision is the kinetic energy of ball A before the collision plus the kinetic energy of ball B before the collision. This is 1/2 mv squared for ball A, which is 0.5 times 4 squared, plus 1/2 mv squared for ball B, which is 0.3 times 0, because it's not moving, squared, which gives us a total kinetic energy before the collision of 4 joules. After the collision, the sum of the kinetic energies is given by the kinetic energy of ball A after the collision plus the kinetic energy of ball B after the collision, which is 1/2 ball A's mass times its velocity after the collision squared, plus 1/2 ball B's mass, 0.3, times its velocity, which is 5, after the collision. This gives us 4.0 joules of energy as well. This tells us that the sum of the kinetic energies before the collision is equal to the sum of the kinetic energies after the collision, and therefore this collision is elastic. Momentum in an isolated system is always conserved. This law is a direct result of Newton's third law of motion, where the change in momentum of one object is equal and opposite to the change in momentum of the other object. The combined change in momentum is 0. Kinetic energy, on the other hand, can be easily transformed into heat, sound, and the deformation of objects. Conservation of energy, or the total amount of energy in an isolated system, does not change, but energy can be transformed into other types, does not depend on Newton's laws. So conservation of energy still applies. In inelastic collisions, some of the kinetic energy may be lost due to friction between the objects could cause some of it to be converted into heat energy. The object was permanently changed. This would happen in a car crash, where the car might be crumpled, or anytime the object is broken, bent, snapped, twisted from its original shape. This includes if the objects are stuck together after a collision, or as you would see in a hit and stick collision. Some of the energy might be converted into the energy of light or sound. These energies are still within the system, they've just been transformed into other types, so conservation of energy still applies, while kinetic energy is reduced. In the real world, it is impossible to achieve a perfectly elastic collision. There will always be very minor, very tiny deformations of any object in a collision, and there will always be some sound, heat, or light energy released. However, collisions between two hard objects, such as billiard balls or steel pucks, or later in Physics 30, we're going to look at collisions between subatomic particles, such as electrons. These collisions come very close to being elastic, and we can treat them like they're elastic collisions when we're doing our calculations. Another example, and in this case we have a hit and stick collision. As I've already told you, a hit and stick collision will always represent some kind of deformation of the object or change in the object's shape, and as a result they will always be inelastic. But we're going to show this through our calculations in this example. Billiard balls A and B stick together after the collision. Calculate their velocity after the collision and determine if it is elastic or inelastic. We're going to start by using conservation of momentum to determine their velocity after the collision. Conservation of momentum says the sum of the momenta before the collision equals the sum of the momenta after the collision, or momentum of ball A before the collision plus momentum of ball B before the collision equals the momentum of the two combined balls, or momentum AB, after the collision. Since momentum is given by the formula mass times velocity, momentum of ball A before the collision is its mass times its velocity, plus momentum of ball B, and since ball B is not moving, its velocity is 0, so its momentum is 0 before the collision. After, the combined mass forms the momentum of ball AB. The combined mass is 0.5 plus 0.3 is 0.8 kilograms times the velocity of AB after the collision. This tells us 2 plus 0 equals 0.8 VAB after. Or VAB after, when we rearrange and solve, is equal to 2.5 meters per second. That's the first step of the problem. The second step of the problem is to show whether the collision is elastic or inelastic. The sum of the kinetic energies before the collision is the kinetic energy of ball A plus the kinetic energy of ball B, both before the collision, or 1/2 mv squared for A plus 1/2 mv squared for B. So EK before the collision is 1/2 0.5 times 4 squared plus 1/2 0.3 times 0 squared, which is 4 joules. The sum of the kinetic energies after the collision is EK of ball AB, now that they're combined, after the collision. 1/2 mv squared for ball AB is 1/2 0.8, because their combined mass becomes 0.8 kilograms, times the velocity we found in the first step, 2.5 squared. This gives us a total kinetic energy of 2.5 joules after the collision. And since the sum of the EK before the collision is not equal to the sum of the EK after the collision, this tells us that we have an inelastic collision. The hit-and-stick collision shown in this example is considered to be a perfectly inelastic collision. This is because it is mathematically impossible to have an elastic hit-and-stick collision. All hit-and-stick collisions are referred to as perfectly inelastic collisions because of this property.